Hi, welcome to this new video. This video is on influence line diagram, what we call ILD. Okay, what do you mean by ILD? The influence line diagram is a diagram which represents the variation in a force component. Let's say it could be a reaction or a shear force or a bending moment due to a unit load or a set of loads traversing a structure. That means if I allow a unit load to traverse a structure, okay, from to the left hand or right hand to the left hand, how does the location of this unit load change a particular force component, say reaction or shear force or bending moment? Okay, so it could be due to a unit load or it could be due to a set of loads. By the way, why do we need that? Because say, let's take a simple example and then we'll figure out why it is required. Let's say we have a simply supported beam and I am asking you, where can I place a concentrated vertical load of a particular magnitude so that I can get a maximum bending moment at the midspan. Okay, if I ask the question immediately, you will be able to tell that if and only if you keep the concentrated load at the midspan, you get a maximum value of the bending moment at the midspan. All right, so that is straightforward answer. However, say I give you a couple of forces, concentrated loads again, with certain distances between them, with certain magnitudes. And then if I ask you the same question now, right? I'm giving you a set of concentrated forces, and then I'm asking you what is the ideal position of this particular set of loads such that you get again the maximum minimum at the midpoint. Will you be able to answer straight away? May not be, right? So that's what this influence line diagram addresses. We are going to systematically learn the way in which this question could be addressed. Okay. So we have seen that it could be a reaction or shear force or bending moment, right? So first we will take the case of a reaction and then we will see the case of bending moment and shear force. Right. We'll just start with the simple example of a unit load and then we'll move on to see what happens with a set of loads. So I have a simple sort beam here and then I want to construct the influence line diagram for the reaction VA and VB. Okay. So in order to do that, what do we need to do is we need to place a unit load at some location, random location, which is x unit from the left support. It could be from the right support also, right? I, I mean, you can allow the load to traverse from this end to the right end, or you can do it otherwise also from right end to the left end also is possible. I am considering this way. So in this configuration, we need to get the expression for the reaction VA and then VB, right? It's straightforward here. Just how do we do that? You just write. If you want the reaction here, you just take this. This is L minus X, right? So you write L minus X by the total span. So from that you get this, right? Similarly, if I want the reaction here, you just take this span divided by the total length. So X by L, right? So it's straightforward. Now we are going to plot this expression. So it's the equation of straight line. Directly we just require 2 points to complete the straight line. If we substitute x equal to 0 here, we'll get a value of 1, which is the ordinate here at the left hand. And if you substitute x equal to which corresponds to this point B, you get a value of 0, right? So I have 1 point here, another point here, just connect by a straight line. So that gives the influence line diagram for VA. That is, if a load of magnitude 1 starts going from left hand to the right hand, right? Depending on where it is placed, it's going to give me a value of reaction according. That means if I place the unit load here 1, I'll directly get the reaction 1 here, right? So that's what this particular location x equal to 0 gives. Let's say now I'm going to place this load exactly at the midspan. Okay, so in that case, x will be L by 2. Substitute that L by 2 here, this expression, you will get that it gives a value of 0.5, right? So that is the value of reaction. How do you get that from the influence diagram? You go to the location of x equal to L by 2 and then see the ordinate. So this is the midpoint, this diagram. So it will give you a value of 0.5. Say finally I'm going to place the load here at the right end, right? So if I keep it here, you know that this support is going to take the entire load. So this is going to be divided off any reaction, right? So for this particular location, x is equal to L, right? So substitute it here, it will give you a value of 0. Okay, directly that's what you infer from this point here. So that's how it works. Similarly, if I'm interested in knowing how the reaction at the other end will be, I mean, this reaction varies because of the placement of this unit load. This diagram gives the answer to it, right? So again, if I place the load here, what should happen for the reaction here? It's not going to produce any reaction, right? So x equal to 0 is the location here. So go to the inference diagram for the reaction will be, it will give you, the ordinate will give you the value of the reaction. Similarly, if I place the load here at the midspan, again it is going to take off of this share, right? So if I go to the corresponding location of the influence line diagram for the reaction VV and find what is the ordinate, it will tell me what is the reaction. Okay, because of the placement of this unit load at the midspan. Similarly, if I keep the unit load at the right extreme end, this suppose is going to take the entire share. So I need to go to that location and then see what is the ordinate. It tells the thing. It's saying the unit load will produce a reaction of 1 unit to the right. Okay, that's how it works. Oh, so this is the case. Now we will go to the case of the cantilever and then see what happens to the reactive moment this time. Okay. So I'm going to allow this unit load to traverse from the right hand, sorry, left hand to the right hand, and then I'm going to find out what is the reactive moment at the NB. Okay. So again, you can do the same, you can follow the same step, right? So place this unit load at random location X, and then if you get the expression for the reactive component of your interest. In this case, the reactive component what we are interested in is the moment at the location B, right? So for this placement, you can see that the reactions are as shown here. The shear force is, sorry, the reactive force at the right end is 1, and then the reactive moment is L minus X. So this is the expression you require to draw the influence line diagram for the reactive moment MB. Again, this is the equation of straight line. Substitute x equal to 0, it gives the value of L, so that is this ordinate here. And then say x equal to L, if I substitute, we are talking about this end, right? So x equal to L, if we substitute, gives a value of 0. So that's what this location is. You have 2 points, connect it with a straight line. And then mind that I am drawing it on the negative direction, right? Why you do that? Because to the right end, okay, I mean, this is the notation we are following. This should be the way to call a moment, a bending moment, positive. I think, however, I should have probably drawn it this way. Again, it depends on whether I call clockwise moment positive or counterclockwise moment positive, because this is about reactive moment in particular. But what I was saying is regarding bending moment as such. Okay. So let's say maybe at least for this video, let's say I'm saying clockwise moments, external moments, right, are positive. Maybe in that sense only I can say that this should be drawn in the negative direction. Right. I'll clarify this point in the upcoming video further. Let's move on to the bending moment. Okay, so second case is the bending moment. First we have started with the reaction. Next we are moving on to the bending moment. Here, mind that this is a reactive moment here, right, in the previous case. So for that, we are going to take the cantilever beam again, but it's going in a different manner a bit here. And now I'm going to draw the influence line diagram for the bending moment at this location C, which is A units away from the left hand, right? So in order to do that, we're going to place the load at a random location 1, okay, and then X units away from the left hand. Mind that here in this case, we got to place this load at two different locations. I mean, there are two cases here for x less than a, and the other case is x greater than a. Because depending on whether the load is placed here or here, the nature of bending moment will change. Okay, that is the reason why we have to do this. So initially, if I place the load here, that is for x less than a, I see that the bending moment at this location is 0 straight away, right? because only this portion is going to bend, this portion will remain straight line. If you draw the reflected profile, you will see that there is no bending moment here at this location. See, when the load is placed within uh, a distance of A units, right? But what happens if I go beyond the point A? That is for x greater than or equal to A, you get the expression for bending moment as A minus x. How do you get that? You place the load here, okay, that is beyond A and mark this as x. And then you need to uh, first get the reactions and then you need to see what is the expression for the bending moment here at this location, C of our interest, right? So if you do that, you will see that the expression for bending moment at the location C is A minus x, right? And then you need to plot this here. So already for this span AC, we have seen that the bending moment will be 0. However, when it crosses, and then it will crosses this point C, it's going to cause a bending moment at the location C, which varies the manner what we see here, right? So this is the influence line diagram for the bending moment. The last one is the shear force. We have overhanging beam here. So again, here we will have to consider several cases. First, we will consider span 0 to B. So that is, if you keep the unit load in this span, what is going to happen is the case. That's what I'm doing here. Initially, I'm placing this unit load here and I'm marking the distance x here. And then you need to use the ideas of statics. Okay, use equilibrium equations and then determine the expression for the shear force at this location E, because that's the location we are interested in. I'm trying to draw the influence line diagram for the shear force at this location E, right? So in order to do that, I have first obtained the expression for the reaction here, VB, and then I have drawn the free body diagram to get the expression for V. Okay, so this is again the equation of straight line x minus b by L. So this variation is shown here. That is that equation is depicted here, right? So this is the influence line diagram. For this case, is for the load being placed within this span L, right? Next, we are going to allow the load to traverse between this span B. Okay. Again, I'm marking x from the left hand, and then in this case, I'm first determining this reaction VC using the equation of static equilibrium, right? And then I'm getting the expression for V, which is the shear force at the location E, right? See, after this, I have already drawn. This time, I'm just going to draw only for this span B. Okay, so this is the equation what we have here, right? Just we need to plot that. Similarly, next place this unit load in the span EC. Okay, now I am finding the reaction at this location, which is VB, and then I'm getting the expression for V. All right. So here we see that at this location there is a jump, right? Because I get different values here. For instance, in the previous case, if I substitute, see, I can use the extreme value as b plus a, right? So when I substitute b plus a here for, for x, b plus a minus b by l, which will give you a by l. That's why I got this ordinates value here at this end. Now I have this expression here. So the initial value is b plus a, right? So that's what starts from here. We substitute b plus a here, b plus a minus b minus 1 by l. So you'll get b a minus a by l minus 1, right? So from this expression, you get a by l minus 1. So mind that a by l being a small value will be positive when I just write a by l, but when I subtract minus, when I find a by l minus 1, we get a negative value. So that's why it flips to the other side here. And then the extreme value is b plus l, which corresponds to this point C. If I substitute b plus l here, you just get a value of 0. That's why at this location we have a value of 0 here. So finally we have the span CD, same procedure. Either included certain location in this span CD and mark x units and then get the expression for shear force here. So I have got the expression for the reaction at this location C here first, and then I have got the expression for V here. So again, you need to plot this. The least value it takes is what? B plus L, and then the extreme value it takes is B plus L plus C. So you need to substitute those two values. When you substitute B plus L, you get a value of 0, and then when you substitute B plus L plus C in this expression, you get a value of C by L. Okay? So that's how we complete the diagram for this span sail. That's all. I have just drawn this here, just an exaggerated view to show the influence line diagram for the shear force view. Right. That's all as of now. We'll meet in the next video and we'll learn further about this influence line diagram. Thanks a lot.